Introductory circuit theory teaches us that power sources are perfect. We treat them as frictionless energy pumps that provide a stable voltage regardless of the demand placed on them. That ideal model fails the moment you build a physical circuit. Real electrochemical cells are constructed from viscous electrolytes and physical electrodes, and these materials possess inherent physical limitations. To understand why circuits fail in the field, we have to discard the ideal battery model entirely. We are going to build a complete mathematical model of a physical cell from first principles. We will do this in 3 steps. First, we define static electromotive force. Second, we map the dynamic internal resistance during operation. Finally, we will derive the algebraic formulas required to calculate these hidden internal variables. Relying solely on whiteboard schematics ignores the thermal and voltage constraints that define how a device actually behaves once it moves into production. To understand a cell's base potential, we must examine its internal anatomy. This diagram illustrates a physical cell containing an electrolyte fluid and 2 submerged electrodes, labeled P and N. We are starting our analysis in an open circuit condition. As the text indicates, the current, I, is exactly 0. Absolutely no external current is flowing. In this static state, a specific potential difference exists between the positive electrode and the surrounding electrolyte, defined as V sub P minus V sub A equals V plus. Simultaneously, a separate potential difference exists between the negative electrode and the electrolyte, written as V sub N minus V sub B equals negative V minus. To find the total potential difference across the terminals, we combine these values. The math shows that the terminal difference equals the sum of the potential differences at both electrodes, plus any potential difference across the electrolyte itself. Because no current is flowing, the electrolyte potential difference is 0. The final sum of the electrode potentials is formally defined as the cell's electromotive force, or E. Note that this electromotive force is not a measure of flowing electrical power. It is a static, theoretical maximum potential dictated strictly by the cell's internal physical chemistry. To analyze the cell under load, we abstract that physical chemistry into an electrical schematic. The physical cell becomes an ideal voltage source, E, placed in series with a small internal resistor, lowercase r, which represents the electrolyte's physical impedance to ion flow. We can observe this dynamic state in the top schematic. The red arrows indicate the cell is discharging, acting as a power source pushing current out from the positive terminal into an external load. As that current pushes through the internal electrolyte, it creates an unavoidable internal voltage drop. Mathematically, this drop is the current I multiplied by the internal resistance, R. This establishes the primary rule of a discharging battery. The actual terminal voltage available to your circuit equals the static EMF minus that internal voltage drop, IR. Now look at the lower schematic.
This is the charging state, where an external power supply forces current backwards into the positive terminal of the cell. This incoming current must work against 2 forces at once. It has to overcome the cell's inherent EMF and push through the internal resistance drops simultaneously. Therefore, the rule for charging is reversed. The terminal voltage required to successfully charge the cell must equal the EMF plus the internal voltage drop. The voltage rating printed on a cell is a static baseline. In practice, terminal voltage fluctuates constantly, shifting according to the direction and magnitude of the load. This physical limitation presents an engineering problem. Because internal resistance is physically sealed inside the battery casing, we cannot connect test probes directly to it. So how do we measure it? We solve this by building a diagnostic test circuit. Looking at the schematic on the right, we connect our real cell to a known, measurable external load resistor, capital R. For this closed loop, our first mathematical axiom states that the total current equals the EMF divided by the combined total resistance of the circuit, capital R plus lowercase r. Our second axiom relies on Ohm's law. The working terminal voltage across that external load resistor is simply current times the external resistance, V equals IR. We need to eliminate the current variable to link our known external readings with the unknown internal ones. We substitute the first equation into the second, establishing that V equals E times R divided by R plus R. Next, we rearrange the equation to group all the resistance terms on one side. This isolates the ratio of total resistance to external resistance, which equals E divided by V. By separating the resistance fraction into 1 plus R over R, we slowly isolate our inaccessible internal resistance variable.
Finally, we subtract 1 and multiply by R to reveal the derived formula. Internal resistance equals the external resistor value multiplied by the ratio of EMF to working voltage minus 1. Through strategic algebraic substitution, we have engineered a method to quantify an invisible internal physical constraint. We only need safe external multimeter readings of voltage and a known resistor to find it. Let's compare these two states directly. On the left, an open battery measures purely its theoretical EMF. On the right, a closed circuit under heavy load outputs a significantly lower terminal voltage. EMF acts as a theoretical ceiling. The physical presence of internal resistance guarantees that the working voltage during operation will always be lower than that ceiling. This leads to a very specific diagnostic trap. A battery may show its full rated voltage on a high-impedance multimeter, yet drop below the required operating threshold the exact moment it is asked to drive a heavy physical load. You now possess the exact mathematical tool to predict and calculate that internal voltage drop before you ever solder a component. Mastering these algebraic models provides the foresight needed to account for internal constraints before they manifest as errors in practical engineering.